Hi, this is not a game dev log, and these are 8 tips for code shortening in REPLICUBE. Obviously this is gonna contain some spoilers, but I'm using the second tutorial puzzle as example. So if you really don't want spoilers, yeah, don't watch this, try it out for yourself. But I'm only gonna use this first thing as example, and I'm trying to use that for explaining the techniques. So we have to build this thing, and this is the naive solution, I would say. I think everybody would start with this. So we have the top half, or a little less than half, which is 1 to 3 for the y, for the green y-axis, and then the bottom half, which is 0, -1, -2, -3. That needs to be orange. So we just check if our y is bigger than that, we return dark blue, and otherwise we return orange. So first let me explain a bit about the token counting. So you can see here, this code is 11 code size, so tokens, and how is it counted? So well, it's broken a bit here, my comments, but I've tried to show it here. So this row is 5 tokens, which means this is 1 token, 2, 3, 4, 5. Then these are 2, 1, another 2, and 1. So this is in total 11 tokens. There's probably a longer solutions to make, but I think this is the cleanest if you don't know any optimization tricks yet. So I've prepared different steps here. So this is step 1, which I call naive. So then we can go to 2, which is a fake ternary. So let me copy paste that here and explain it here. Although this also looks nice, it's, I think, also fun to watch. This is a bit more fun. So this is basically the same as we had before. The logic, we've still check for y, whether y is bigger than 0, and return dark blue or orange, depending on whether this is true or false. So we have 8 tokens here, which is 1, 2, 3, 4, 5, 6, 7, 8. So that's a big improvement. And this is just a trick. Basically every if, then, else, and statement can be shortened this way, because that's a lot of words. As you can see here, just this check with 2 results is 1, 2, 3, 4, and then the double return, so 5 or 6 things that are not needed. So this is 5 tokens that are needed basically, and of course you need some control, but then there's 6 that can be moved down with only 2 here. And how does this exactly work? Well, in other programming languages you have something like return brackets optional, I think, but just for clarity, dark blue. Now I don't know what the character here is. I didn't prepare it that good, but something like this, which is called the ternary operator, because it has 3 parts. It's an operator with 3 parts. So first this gets evaluated, and then based whether this is it's the same. This gets returned or this gets returned. So I'm not sure exactly right now what the character here is in different languages, and this does not officially exist in Lua, but this system, which is not exactly the same because it has some weird things. I think I'm not a Lua expert, but I think the main difference is if this value is false or falsy, it breaks down, because these are basically functions, I think, that, well, yeah, I'm not going to go into that both because it's too long, and I'm not 100% sure about how it works. But this is one big improvement for every if-else statement. So that's the fake ternary. Then step 2, which I've called colors as numbers. So that's improvement 2. Well, this is not a real code shortening improvement, but still an important step. Of course, when I got the demo, this was only the only option, but now the previous one, I typed out the names of the colors, but the colors are just numbers, and that's designed on purpose because that allows you to do math, which is needed in later puzzles to get any result, but here it can help optimizing in future steps. So dark blue is 12 and orange is 8, and as we get to the end, we are going to find out that this is not random. So this is something to keep your eye out for. So the developer of the game clearly has chosen these numbers with a reason, because first I thought, well, it's just fun colors and it's fun shapes. But when you start golfing, you can clearly find out that he did this with... golfing is just another name for shortening code. He clearly did this with code golfing in mind, because these specific numbers and sometimes other parts of the things make it sometimes more easier in this case to make the code shorter, but also make it a lot harder. For example, if it was this shape, I think it would be a lot easier to get to shorter things. Not 100% sure, but the fact that the 0 goes down makes it a bit harder. So this is just an intermediate step of preparations for doing math. So then this solution I call math based. So let me first paste this and let me show that this is still the same result. So all these are just different ways to get to the same result. This is just a comment, so let me put it a bit more distant from it. So this thing is 9 tokens. So actually it got worse, but it's to show two things, this intermediate example. One of them is, so you cannot do math on booleans. So I'm not sure how in depth I have to go, but a boolean is the name for something that can be either true or false, and then a number is a number. There's more details from that, but and often true or false is also 0 and 1. Well, the other way around, true is 1 and false is 0. So you can do math in languages like C, but here if we remove this, we get an error saying attempt to perform arithmetic on a Boolean value. So this results in either true or false, and then we cannot just do math. But then if we check the documentation here, we can see there's the function b to I, Boolean to integer, which then turns this into a 0 and a 1, and we can do math. So and this whole thing shows us two things. One, functions are quite expensive in terms of code size, because again, same as with the if-else statement, this thing is counted as a 1 token, and then the opening bracket is counting as a token. So the closing bracket you get for free, but this is already 2 tokens for just calling a function, and that is quite expensive. So there are also some tricks I thought about. There's also, for example, the function, well, you can check them out yourself here if you already have the game. There's the function sign, which feels like it helps, which returns 0, 1 or -1, depending on the sign of the input value. But again, this is very expensive, and seal and all this kind of stuff, floor rounding, and then especially if you have multiple parameters, it gets even worse. I think the comma is free as well, but still this is worse. So that's one thing that we learn here, that functions are quite expensive. And the other thing is, well, basically if we want to go the math route, we have to find a way to get in less than 1, 2, 3, 4, 5 tokens some formula that gives us a different number, preferably 1 for these 3 values. So for when y is 1, 2 or 3, it should return 1, and then if the value is something else, 0, -1, -2, -3, it should return 0, or at least any 2 different values, but then later you can solve this with math. One thing I didn't show, I think, is the world records. So when I recorded this previous optimization video, did I tell about that? Maybe not. So I did this 45-minute video where I tried to figure this out, and then I thought, well, it's better to do a video on my conclusions. But the world record then was 3, but that's deleted, and I already suspected that was a hack. So the world record is either 6, if these are not hacks. I'm going to 6, so I'm not sure if 5 is legally possible. It could be, but it's very hard to imagine, I think, because that's not a thing here. So what's the absolute minimum? I think, well, return is already 1 token. Of course, we have to use Y. I think it's impossible to not use Y, so that's 2 tokens. And then if we want to get to 6, then we need 2 numbers, which makes sense because there's 2 different values. So we have to always use 2 numbers and 2 operators. So I think it's very hard to imagine there being a shorter code, but maybe there is. Let's go to the next step. So here, let me also just copy this. I'll try to put this in the description maybe. If not, remind me in the comments if I forget. So here, like I was saying, I'm trying to use math to get something that gives us either 2 different values on this exact border of 0 and 1. So this formula still gives us the same thing. Of course, we need this brackets here, but that's the next step. So let me show you what this, or explain what this double slash means. So the single slash is division, and the double slash is kind of integer division, but which means that it's always converted to a whole number. But more specifically, this is the floor division. So what it does is it does the normal division, but then it does floor, which means it rounds down, even if it's below. So here I put the 3 examples to show how it works. So when y is 1, of course I do in this example, I already add the negative sign here. So if y is 1, this whole thing becomes -1 floor division 4, which comes out to, the division comes out to -0.25, which is floored to -1, and then 0 stays 0, and 1 becomes 0.25, and also becomes 0. And then this is kind of interesting. Also part of what makes the puzzle good, I think, is it immediately breaks down when we go outside this range. So for 4, this would become 1 or -2, etc. So, but we do have for this exact range split the output of this into 2 numbers. But then we need some math to put it to get to return 12 and 8. So we do -2. Well, we see the whole formula here with these 2 options that come out of this part. So -2, -1, and -1 minus 2 is -3 times -4. The negatives cancel out, so that's 12. And then here it's -2. -2 times -4 is 8. And here is also, it's a bit annoying because it would be easier if this was 1, if this was +1 for the positive half, but now we need a lot of fiddly things. Well, that's the next step. So that step where we get rid of functions because functions are too expensive. Of course, we've gone from 8 bits, 8 tokens to 9, and then even to 10, but sometimes that's needed because this was a dead end. There's no shorter way. There's no tricks to get this type of direction shorter. So we have to search for new directions. So then we also can conclude, well, we need to get rid of these brackets, parentheses. So here's the version without parentheses. So what is the biggest difference? Well, of course we have order of operations. So in this version, this is handled first. So this is negated. Then we have the division. Then we have this subtraction. And then we have this multiplication. And here we get rid of this first negation, that's the biggest change. So because here we do, yeah, this is basic algebra. Is it called algebra? I think I have good intuition for math, but I'm not very good with the terminology. But basically we take out this outside the brackets, and that's because it's multiplied by 4. Here it becomes an 8, and we see indeed that it has the same output still. So this all becomes the same, and now we're back to 9 tokens, just because now we don't need any brackets. And then here I prepared the fact that of course you can add this 8 to the front, which brings us, so this is a very short step to get rid of the parentheses by just changing the numbers and taking the subtraction out. And then here we take the free, this is called free negative in my terminology. So this is a bit tricky of the token counting. So we have 9 tokens, this is 1, and the negation is 1, so 2, and then y, 3, 4, 5, 6. But this counts as 1 token, 7, 8, 9. And so that means that a negative number is 1 token, at least up to a certain size. But negation on a variable is a separate token from the variable. So that means that there's some gains to gain by reordering again all this stuff until we at the point that the negation is not anymore for the variable. And in this case that means we can change this formula to this formula, and it saves us 1 more token, because the negation went from here basically to here, which makes it a free negation. I think apart from that, this is not too interesting. Well, you can divide by negative numbers, of course, and that also flips the same thing. So now we are back at the 8 tokens with a big roundabout way that we already had in step 2. But I think we learned a lot. I learned a lot of new tricks, and of course this is a very simple build, and if you want to optimize bigger builds, more complex cubes, then maybe all these steps are needed or are good tricks. So then we go to the next step. Does this fit the screen? It does. So, and I must be honest, so I got stuck at the previous episode, and I was quite happy that I got 2 or 3 different ways to get the same result, because that means to get a good result, very different with 8 or 9 tokens, because that means that there might be a chance for more, and it also means that it's a very fun puzzle if you like coding, etc., etc. So then, actually, to be honest, so I was trying to Google the answer because I couldn't handle not finding the 6 solution, because and the biggest issue was I wasn't sure whether it was just a Lua quirk that I was missing. So, but I couldn't find any results, and then I actually asked my good friend ChatGPT, and he was thinking for a long time. And a spoiler, he did not find the answer. And this is, I think, a very good use of AI. But of course, this sometimes is controversive. But he helped me come up with this idea. So. But first we need to explain a bit of this bit hacking, because now we get really into the depth. So this is not Lua specific, this is just code specific, I think. So first, so this is a 7 token thing that still returns the correct shape. So 1, 2, then we have this new token, which is the bitwise OR operator. Sadly still a negation sign, that's 4, 5. This is the bitwise AND token, and then a 7th token is this. So all this bitwise stuff is easiest to understand if you take the bitwise representation of the number. So these are all possible values of y we care about. And then of course, because it's negated, they get swapped around, basically upside down. So the way I'm ordering this here is the exact opposite way that they will be here because of this negation. So bitwise 0 is just a big line of zeros. So these 2 dots means, well, there's a big amount of zeros. If it's a 32-bit, and it doesn't matter for this puzzle, 32-bit number, there's in total 32 zeros. If it's 64-bit number, 64 zeros. And then if we go to the positive side, to get 1, we swap the last bit. So the last bit, the least significant bit, to 1. And then if we want to go 2, well, it looks like 10, but this is 1 0. Well, there's more tutorials on how bit representations work, so I'm going to go over a bit quick. And then this is the bitwise representation for 3. So one thing that you can see here is that odd numbers, that helps sometimes. For other tricks, have always the last bit 1, and then even numbers have 0, etc. So you can kind of see a pattern here. And then this is more complicated, and I even had to look this up again. I've learned this very early, but you rarely need it except for these crazy situations. Is then for negative numbers, there's something that's called, and I'm not even sure if I'm going to type it correct, 2's complement. Yeah, also hard to, it's not something that I can explain very easily because I'm not fully grasping it, but basically if you just look at the patterns, so now these dots means this is filled with ones, and the pattern you can see is this mirrors, so everything that's a 0 here becomes a 1, and then these two values have the same thing, so everything gets flipped from a 1 to a 0 and vice versa, and here as well. Of course you see there's a tiny offset, so you would expect that maybe -1 and 1 positive 1 gets flipped, but there's a little offset, but that makes the pattern so nice. So that's the representations, and then the other 2 or 3 numbers that we care about are 4, 8 and 12, and this is why I said earlier that this puzzle is quite nicely designed, because the 8 and the 12 and the 4 have very specific bit patterns. So for future puzzles you can also try to pick that out. So the order of operations is, do I even know, and does it even matter? So the negation comes first. So I think the actual operations would be first the OR operation, but I prepared it the other way around, but maybe I can do it like this because I think that's the correct thing. So OR, the bitwise OR operation means that if you have 2 numbers, so for example 8 and I don't know 2, then you compare the bits here, and then all the bits get set, so it becomes a 1 if either of these is a 1 or if both are a 1. So we can already see that for all these values, so basically that means that if either 1 or both are a 1, it gets set. And what that means, because this one is just full of zeros and only a 1 at this specific spot, means basically that only this thing gets set for every value. So I'm going to do it here to see what it would be. So the OR 8 specifically means that just the 1, 2, 3, 4th bit from the right always gets set to 1. So that's what this does. And then the AND is basically the other bitwise operation. That means that again we are going to compare these two bitwise representations, but then we return a 0 when either one contains a 0 or both, and we only return a 1 when both contain a 1. And that means that for this specific pattern, again, there's only 1 bit set. So this is like a filter almost, which only lets through this bit. And we can see that exactly for these 3 values, this is 1. And for these 4 values, this is 0. And that's exactly what we need, except the opposite way. That's why we add the negation sign. So these two combined first, in my head it makes more sense that we do this first, but it doesn't matter. So this one filters out and only makes this bit a 1. And then this one always adds a 1 in this spot, no matter what was there before this together. And then we either get this thing when the filter only returned a 0 and we added the 1, which is orange. And when this returned a 1, then we also add this one, which coincidentally, but not coincidentally, returns 12, which is dark blue. So that's a quick, maybe not so quick explanation about bit fiddling, and it is needed. So that's one thing for me that I learned about this game. So if you're happy to go fully into this bit fiddling, then this is the game for you, but you also have to be careful with order of operations. And then for the last step, because we need to get it to 6, we have this solution, which is the 6-byte solution. And what's the biggest change? Again, we needed to get rid of this negation. So we have the same amount of operators. We have two numbers, two numbers, two operators, and then y, but here we had the negation. So as you can see, we put the negation as similar with the earlier steps. We changed the negation from y to the 4 basically. So if we first take this step, now minus y is the the 2's complement. So this is and now I've added a bit more space here, but it's a lot of 1's, and then only the last 2 are 0's, and that means that we filter. Yeah, it's now not so much a filter where we just only let through one of the values, but it's the other way around. We basically set to 0 because it's the AND operator. Doesn't matter what in the other value is set, it will always set to 0. So this operator basically sets every last part to 0, which of course we can see that for both results that's what we need. And then the 11 plus y, yeah, I don't have an intuition for why it works, but it works, and it's just a random quirk almost, it feels like, of these numbers. So these are the inputs of y. So this was -3, -2, -1, 0, 1, etc. But we added 11 to it. So here you can see it in decimal numbers, and here you can see the bitwise representation, and we can again see this pattern that in this third bit, the top 3 are 1's and the rest are 0's, and then again this would fully break, because if I can do this from the top of my head, the bitwise representation would be something like so the pattern would immediately break. So if the cube would extend here, it would be again dark blue, but it's not. So that means, and also we can see it would not be dark blue, because also for this exact range, these bits are so the 4th bit is just always on. So that's almost a free given. And there is some relationships between adding and ANDing and multiplying and ORing or something like that, which I'd have to warm up a lot in my head to figure out. So maybe that's maybe that's also part of the puzzle, the fact that we add exactly 11 and this is the representation of 11 might also have something to do, but maybe that's for a future episode. So I hope that helps get some inspiration for future puzzles, how to optimize that. And in any case, I think this is for random programmers interesting, and especially if you want to optimize code for shortness, brevity in REPLICUBE. So if you have any more questions or any more ideas, leave a comment, leave a like, subscribe, and in any case, thanks for watching.